All right, this is the final review from days 1 through 6 before the winter break. All right, let's get started. So we want to find if these lines have the same length. We did that a few ways. One was using Pythagorean theorem. So I've already marked everything up. So for CD, we can see that we have a run of 1 and a rise of 4. So Pythagorean theorem just says, let's do a squared plus b squared, right? And we're trying to see what this equals. So 1 squared is 1, 4 squared is 16, so this is going to equal 17. Now really this is equaling c squared, right? All these are c squared. So the length of CD is actually the square root of 17. So that's what this equals right here, is the square root of 17. Okay. And then we can do the same thing for EF, which is right here. So I'll do blue. And that's going to be 2 squared plus 3 squared, right, which is 4 plus 9, which is 13. And likewise, these are also what's equal to c squared, right? So that means c actually equals square root of 13. So then clearly the answer would here to this question, determine if the following lines have the same length. The answer would be no. This one's square root of 17, this one's square root of 13. So our answer would be no. Okay. Then we can do the same thing for the next two. We have let's see here, GH and JK. So GH would be 4 squared plus 2 squared. Okay, so this will be 4 squared plus 2 squared, right? It's equal to c squared. So we have 16 plus 4, which equals 20. Therefore, c is going to equal the square root of 20. Okay. So up here we have square root of 20. Okay, and then we have JK here, which is 1 and 4. So it's very similar to CD here. So it'll look identical and be the square root of 17. So go over here and say c is equal to square root of 17. So these as well are not congruent. All right, so that's one way to find the distance between 2 points. When you have a graph and squares you can count, this is the easier of the 2 ways. The other way we looked at was when we have not a graph and we have to find out, well, how far apart are these numbers from each other, and then calculate using this, which is the distance formula, which is basically the same thing, right? So if I just know the 2 x values, the 2 y values, find how far apart they are from each other by subtracting, square them, and then we can go ahead and solve. So my 2 x values are going to be -3 and 0. So I'd say -3 and 0. My 2 y values are 2 and -8. So we have what, -3 minus 0, which is -3. We have -2 minus -8, which is +10. Right, so that comes out to 9 plus 100, which is the square root of 109. Okay, and if we wanted to use a calculator, we could find out approximately what that distance is, but I know the square root of 100 is 10, so I expect this to be a little bit bigger than 10, so like 10.2, 10.3, if we need an exact distance. Okay. Now keep in mind on here, all I did really this Pythagorean theorem, right? We found out how far apart are the x values, just like we count here. How far apart are these? They're 1 apart, right? how far apart is -3 from 0? It's 3 or -3. Then we counted, how far apart is 2 and -8? Well, those are 10 away from each other. So it's the same thing as a graph, so that's why this formula and Pythagorean theorem look very similar. They're really the same thing. All right, then we looked at finding the midpoints. Okay, so if I want to find the middle of 2 points, okay, so I just need the 2 x values, right? And I can add those up, and it's really finding the middle of something is like finding the average. So the 2 x values are 5 and 2. Find the middle. What's the number in the middle of 5 and 2? And then for the y values, what is the number in the middle of -3 and +4? And of course, these can be decimals. You always want to write them in coordinate form like this as well. So we have 7 divided by 2, which is 3.5 or 3.5. Then we have -3 plus 4 is 5. Oh, no, -3 plus 4 is 1. 1 divided by 2 is just 0.5. So that's the middle. If we were to plot this, that's the coordinate that's in the exact middle of -5 or 5, -3, and 2, +4. Okay, then we looked at some of these problems with linear pairs, which of course have a sum of 180 degrees, right? Because it's a straight line. Straight lines have 180 degrees in them, right? So we have these two angles, right? 2x plus 23 and 4x plus 1, right? And since they together make a 180 degree line, we can just simply add these together and solve. We've got 2x plus 23 plus 4x plus 1 equal 180, right? So we're going to get 6x plus 24. Yeah, that's 180. I'm going to subtract 24 from both sides. That's going to give me 156, I believe. Yeah. And then we're going to divide both sides by 6, and we'll have, let's see here, a calculator. Let's see, divided by 6. Got 26. So x equals 26. So if x equals 26, we can double check our answer and make sure that our two angles add up to 180. So if I plug in 26 here, so 26 times 4, oh, I'm going to do it like this. Plus 1, this comes out to 105, all right? And then I do 2 times 26 plus 23. I get 75. So sure enough, 75 and 105 do make 180. So that's the way you can check your answer. Make sure you plug it back in, and these actually check out to be a linear pair. Okay. Over here we have a segment bisector, right? So that just means when you have a bisector, mathematically that means this angle, the red angle, is cut in half, right? So that these two are now congruent. The pink and the green are now congruent or equal to one another. So we can say, because it's a bisector, both angles are equal to each other. And we can solve this. So we'll have 45 equals 2x. All right, so x will equal 45 over 2, which is what, 22.5. And just like before, I could plug in 22.5 times 2 is 45. 45 plus 5 is 50. And that's the same thing as over here. So I know both angles do come out to equal 50 degrees. All right, so that was the first few days. Then we moved on to transformations, and we just had to plot these. So like 2, let's see here, 2, 4. So we got A, B, and C. And then we have some transformation that just says right here, it means x minus 4. X is left and right, so minus, right, will be left. And then y is up and down, so plus will be 1 up. So we're just basically moving this, each of these points, 4 left and 1 up. So I can just count these out. 1, 2, 3, 4, up 1. So that's going to call that B prime. 1, 2, 3, 4, up 1. That's A prime. And then 1, 2, 3, 4. And there's C prime. Okay, so that is our transformation under this translation here. Okay, looks just like that. Remember, these are all rigid transformations, meaning the size and shape should be the same. So if you get an answer that looks bigger, smaller, or in a different shape orientation, something's wrong. Okay. Over here, same thing. We can just transform this. See, 2, -1, that'd be right here. So this is P. 2, -3, down here, this is Q, and this is R. So this is going to be 3 left. This is going to be 1 down. So each of these I just moved 3 left. 1, 2, 3, 1 down. So that's P prime. 3 left, 1, 2, 3, 1 down, Q prime. Right, and then 1, 2, 3, 1 down, there's R prime. Right there. And let's see here. There, there, and right there. So there's my transformation. So these are translations, which is basically sliding left, right, up, and down. That was the first type of transformation we learned. And then we moved on to reflections. So if we reflect something over the x-axis, right, that means we actually draw your line of reflection. X-axis is right here, and each point's going to be the same distance away. So if this is 1 away, then its reflection is going to be right here. Okay? So if this right here is 4 away, right, then the reflection down here will be 4 away as well, right here. And of course, they'll be the same size and shape, just in a different location. So that's what a reflection over the x-axis will look like. Let's see, I can do this. Okay, so there's my reflection over the x-axis. Now, number 10 is actually something we did not cover just because of time and distance learning, trying to not make it too complicated, but we can actually reflect over any line. So you can imagine here's the line y equals -x, just a diagonal line going down. If we wanted to reflect it, we could say, well, this point will end up right here, this point will end up right here. It's kind of like a rotation. It looks very similar. So if you wanted to try that, right, it definitely would feel familiar. It's not too different from what we already know. Okay, so it would just look like this. But don't worry if we don't know the negative x's and the positive x. That's fine. We're just doing x-axis and y-axis. So here's the other one, the y-axis, right? So like h will just be 1 away, but on the other side, that'd be h prime. This is 3 from the axis, so this will be 3 here. This will be c prime. And we just keep replicating that same pattern. Let's see. 2, this is 1, 2, 3, 4, 1, 2, 3, 4. Yep, there we go. Okay. Oh, take it online. There we go. So here's our reflection. So you notice I'm not trying to look at it and try to figure out what it looks like visually. It's really mathematical. You want to count the actual squares and make sure it's exactly the same distance from the line of reflection, right? And of course, if we just to have good form, we should probably go in here and actually label these as that's H prime, this is C prime, M prime, and A prime. Oh, no, that's the other way around. A prime, and then M prime right here, just like that. Okay? All right, now let's do some rotations. Okay, so we did this a couple different ways, right? We can do this geometrically or looking at it, but analytically is usually a little bit easier. And you had a cheat sheet on this, I think. Lesson, yeah, 7 transformations. There it is, coordinate rules. So if you use this, it's definitely a lot easier for the rotations. Okay, so they're all right here. So right now we're doing counterclockwise 90 degrees. So counterclockwise 90 degrees is negative y comma x. Okay, so you can write that down, negative y comma x. That's what we're trying to do. So for instance, point P is 2 comma 1, right? So 2 comma 1. So if I use this transformation right here, it's going to be at negative 1 comma 2. So negative 1 comma 2. So that's where P prime will end up. Okay, and we just go through each one. PQ, which is 4 comma 1. Right? So that'll be at negative 1 comma 4. Negative 1 comma 4. That's Q prime. And then lastly, we'll have R, which is 4 comma negative 3. Okay. So that's going to be 3 comma 4. Right? Because negative y, the opposite of negative 3 is positive 3, and the x stays the same. So 3 comma 4. Okay, so there would be a 90 degree rotation counterclockwise. Remember that all shapes are by default rotate counterclockwise. There we go. So it's a little more difficult to visually kind of rotate this, you know, and transform this. Kind of like here, we could just flip it over here pretty easily. But when it comes to rotations, you want to rely on these formulas a little bit better because fewer mistakes are usually made. Okay. So now we got 90 degrees clockwise. So if we're going clockwise, right, that's going from basically quadrant 3 to quadrant 4. That's the same thing as going all the way around counterclockwise 270 degrees. So that's really important to catch that it says clockwise, not counterclockwise. So really, I need to go 270 degrees counterclockwise, y comma negative x. Okay. So this is 270 degrees counterclockwise. Okay, we'll just go through each one. Let's see. D, it looks like it's negative 3 comma 1. Okay, so that's going to be 1 comma positive 3. Double check that. 3. Yep, okay, perfect. And then, oh, it's negative 1 comma 3, so that's over here. And we go E, which is negative 1, negative 1. So that's going to end up as positive 1, negative 1. Let's see here. Oh, wait a minute. Strike that. That's the y stays the same. So the y is -1. Okay. I gotta make sure I got that. Y is negative, and the x is the opposite sign, so opposite -1. Okay. Make sure I got that right. -1, +1. So that's just going to go right here. So that's e prime. Good. Okay. And f looks like it's -1, -1, 2, 3, 4. So -1, comma, -4. So the y stays the same, just moves. So it's -4, and the x is the opposite sign. So -4, +1. So f prime and g. Let's see here. -3, comma, -3. Okay. All right, so we have -3, comma, 3. There we go. And then just connect these and see if, as long as it's the same shape, size, then we're good. Shape here. Let's see here. So yeah, as I connect all these two should look like the same thing, just moved around, right? It's not bigger, smaller, different angles. So it looks like I got everything right there. Okay. All right, we got one more. This time we're going to do just 180 degrees. Okay, 180 degrees. Let's see here. So if we want to use the rules, 180 is -x, comma, -y. Basically just change the signs of both x and y. Okay, so we got -x and -y. All right. So f looks like it's 1, 2, 3, 4, -4, +2. Okay, so that's just going to be +4, -2. +4, -2, just like that. We have h, which is -2, 0. So that's going to be +2, 0. So the 180 degrees, a little bit easier, just changing the signs. And lastly, we'll have k, which is going to be -4, -3. So +4, 3. +4, -3. No, that's -3. -4, -3, so it's going to be positive. Okay, that's up here. There we go. All right. Yeah, just got to get those signs right. Okay. And there's our 180 degree rotation. One way to figure out if your rotation is correct as well, you should, when you connect everything, you'll notice they basically all go through the same spot right here. So the fact that these are all right about the origin means we're in good shape here. So I think I might have made this one a little bit big because it should go through that origin. Let me double check my numbers here. Ah, that's what happened, yeah. Try that. So 4, 3, which is right there. Okay. Yeah, as soon as I did my check, something didn't work. So I knew I could go back and fix it again. Okay. So now let's try the check again. Okay. So here. There we go. And there we go. So see how they're going through the origin perfectly? That's what they're supposed to do. So as soon as I saw it not doing that, I knew something was wrong. Because this is a 180 degree rotation about the origins. So all these need to intersect at the origin. So always good to do a check. All right. Okay, moving on. Just have these problems where we have to fill out a table. Okay, like magic, all of a sudden I put the coordinates up here for our pre-image for both of these, right? And the goal is, of course, to figure out what transformation is needed to transform each of these from the pre-image, where we're starting, to the image, right? So the first step is to figure out, well, how are we going to move this? And there's more than one right way. Usually it's the same transformations, but maybe in a different order. So it doesn't really matter on the order, but one is usually easier to figure out than the other. So if I want to move, let's say, K, right, because of corresponding locations, that's going to have to map to X, right? So K is right here, and we need to get that to be right here. So first thing we probably need to do is reflect it, right? If we reflect it over the x-axis, K will end up right here, and then I'll just need to move it 2 to the left and 1 down, right? And that will put K mapped onto X. Now, we do have to be careful here because these squares are counted by 2, so I need to reflect over the x-axis and actually move 4 to the left, right? From 8 to 4, I have to go 4 left and 2 down. Okay, so let's get that information in there first. Text box, let's see here. We're going to do first a reflection. Okay, and x-axis. There we go, spell it right. Okay, then I'm going to do a translation and slide it over. Okay, now if you need to look up what's the formula for the reflection over the x-axis, you can go back here and see it's x comma negative y. Okay, so I'll have x comma negative y. Then here, remember I need to move 4 left and 2 down. So it's going to be x minus 4 and y minus 2. Let's make that a little smaller. There we go. Okay, so let's just follow that and follow this exactly, and it should work out fine. Okay, so x's stay the same, right? And the y's will change. So let's do this. We'll have 6. Right, this will be 8. This one will be 6. These are all staying the same. This is negative 2. All right. And then here we're going to have the opposite of y. So we have positive 2. So this will be negative 2. There we go. So this will be negative 2 as well. And this one will be negative 6. This one will be negative 6 as well. Good. And then from here, we need to do our second transformation here, which is x minus 4, y minus 2. So each of these are going to take off or subtract 4 from the x. So 6 minus 4 is 2. Right. Here, 8 minus 4 is 4. That's the one we looked at earlier. 6 minus 4 is 2. And then negative 2 minus 2 would be negative 6. Oh no, negative 4. There we go. Oh, I'm subtracting 4. Yeah, negative 6. There we go. Good. And then the y's are minus 2. So negative 2 minus negative 2, negative 4. Okay. Negative 2 minus 2 is negative 4. Then we have negative 6 minus 2, which is negative 8. Okay. There's a delete type. Yeah. And then negative 6 minus 2, which is negative 8. There we go. If I just double check these coordinates and make sure they're accurate. So W is at 2, negative 4. W is at 2, negative 4. That works. X should be at 4, negative 4. That works. Y should be at 2. -8, that works. And then z should be at -6, -8. There you go, and that works. So that way I know, since these numbers that I used just these formulas to figure out ended up matching what I got over here, I know it's accurate and correct. Okay, for the last one, we just need to map MPN triangle to JLK. So I need to go from here over to here. All right, so a couple ways of doing this. You can reflect. Let's see here, I need to get point P to point L, right? So you can reflect this over and then move it up 3, or we can move it up 3 and then reflect over. But either way, we're going to do those two transformations: reflection, y-axis, and a translation up 3. So since we did reflection first last time, let's go ahead and do the translation first. So this is what we call the commutative property works here. Meaning if we translate and then reflect it, or reflect it then translate, you get the same answer. It's very similar to why 2 times 3 is the same as 3 times 2. Sometimes the order matters, sometimes not. There we go. So the translation again was 3 up. So the x doesn't change, so I just write x. But the y coordinates, those are moving up 3. So that's +3. And the reflection over the y-axis is, let's see here, -x, y. All right, here we go. So let's just keep each of these the same. Let's do it this way. Okay, so we'll have -4, comma, and then add 3, so it's going to be 5. Okay. -1, comma, add 3 will be 5 again. Okay, and we'll have -1, add 3 will be positive, no, will be 0. Yes. There you go. Good. Add 3, add 3. There we go. Perfect. And then right here, we're going to do the opposite of x, right? For each of these x's. So negative will become positive. So each one of these, we have 4, 1, and 1. Right? And then the y's stay the same. So 5, 5. Clean this up a little bit. One, which we got what? 0. Yep. And we double check these. So 4, 5. Looks like right there, perfect. 1, 5, perfect. And 1, 0, perfect. So those look like they all line up. And we are set. Okay, so remember these could be in different order. Just depends on your personal preference. Okay, so that's a review of all the problems. Hopefully this helps. Make sure you can do each of these on your own by yourself. Don't just copy them down, because there'll be different numbers for sure on the final, and you need to be able to understand how to do them. Okay, so good luck, and we'll see you the day of the final.